From simulation to reality, exploring autonomous hull inspection. Inspired by ABS's Setting Course podcast with Persona AI, which explored the use of humanoid robots in shipbuilding and inspection, I wanted to take a first step towards understanding what the future could look like in practice. As a quick experiment, I developed a working simulation of a robotic inspection system operating inside a ship's ballast tank, focusing not just on the robot itself, but on the end-to-end pipeline connecting autonomy, sensing, and edge AI. The environment, a digital ballast tank. The simulation models a ballast side tank, one of the most challenging inspection spaces in a vessel. It's got confined geometry, structural complexity like frames, stiffeners, and plating, and limited lighting and visibility. Within this environment, a mobile inspection robot, the Hullbot, is tasked with navigating across multiple bays and performing a structured inspection of the hull plating. Behind the scenes, two systems, one pipeline. What makes this interesting is not just the robot, but how the system is connected. This prototype integrates 1. A simulation environment running the robot and its mission logic, and 2. An NVIDIA Jetson Orin Nano edge computer acting as the robot's brain and onboard AI processor. These two systems communicate in real time, allowing inspection images captured in the simulation to be processed by the edge AI system, mimicking how a real robot would operate in the field. The mission. Autonomous inspection. Once the mission begins, the robot navigates across 4 adjacent inspection stations, aligns itself with the hull structure, scans and captures high-resolution images at each location. At each station, the robot is actively searching for structural anomalies, such as corrosion, pitting, coating breakdown, or fatigue cracks. From capture to classification. Each captured image is transmitted to the edge computer where the AI-based pipeline analyzes the defect and generates a structured output. The defect type, whether it's a corrosion, crack, etc., the confidence score, a severity classification, and a recommended action. At this stage, the classification output is simulated, but the full pipeline, from the sensing to the edge inference, is live and functioning end-to-end. The result, structured inspection insights. The system produces a clear inspection output for each station. The raw inspection image captured by the robot, the interpreted result with bounding boxes, classification, and severity. This shifts the inspection from a manual, experience-based process towards a repeatable, data-driven workflow with the potential for consistent, auditable results. This simulation is more than a visualization. It's a development environment for robotics. It tests autonomy and navigation safety. It refines inspection workflows before deployment. It validates sensing and data pipelines. It accelerates iteration without real-world constraints. Most importantly, it helps bridge the gap between what we think robots can do and what actually works in the field. What's next? From Mujuko to ROS2. While this prototype was built using a lightweight Mujuko simulation framework, the next natural step is to transition towards a more robust robotics architecture using the robotic operating system ROS2. To build that foundation, I recently completed the ROS2 Foundations Architecture, Programming, and Core Concepts course on Coursera. This opens the door to standardized robotics middleware, to real sensor and hardware integration, to scalable multi-node robotic systems, to seamless transition from simulation to real-world robots. The path forward. Looking ahead, I see 3 key areas for evolution. Migrating this simulation into a ROS2-based digital environment, introducing more realistic constraints, lighting, occlusions, sensor noise, incorporating real-world data sets to move from simulated to trained defect detection models. More broadly, this type of platform could evolve into a shared simulation testbed supporting robotics innovation across inspection, maintenance, and survey use cases. Final thoughts. What started as a simple experiment quickly reinforced a key idea. Simulation is not just a demo tool, it's an enabler of real world robotics adoption. By combining autonomy, edge AI, and structured data pipelines, we can begin to build a practical path towards safer, smarter, and more scalable inspection systems in the marine environments.